Welcome back to Math Concepts. We are continuing our work on probability, and we're starting out with the counting principles, which we will use down the road to help us figure out the probability of an event. We've got to be able to count the number of ways our conditions can be met, and we've also got to count the number of things that could possibly happen. And we have a very efficient counting principle to help us do that very quickly. So remember, in this context, we are counting indirectly. We're counting without physically listing things out and doing the counting. Some people also call it the multiplication principle. And in this video, we're going to look at further examples of using the counting principle. So the key idea in this video is being able to use the counting principles to find the size of sample spaces and events. So we'll jump right into things with an example right here. So in this experiment, we're going to form two-digit numbers by drawing from the digits 0 through 9 with replacement. Okay, so you remember what we imagine when we see these words with replacement. Okay, we imagine we have a bucket or a hat or whatever you want with the numbers in there. We draw something out, we look at it, we write it down, and then we put it back in the bucket so it could be drawn out again. All right, so first question says, how many two-digit numbers are possible? Well, you want to make a two-digit number, you need two stages. Remember, the counting principle is all about breaking our experiment up into stages. So you tell me the first digit, and you tell me the second digit. Okay, now, ordinarily, we would have 10 choices here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. However, if we want to make a bona fide two-digit number, we cannot start with 0. Okay, so you have 9 choices for the first digit. The first digit has to at least be a 1. Now you're allowed to use that same digit again. In fact, and you're allowed to use 0. So this is an unusual situation in that we have more options in the second stage than we do in the first stage. But that gives us 90 possible two-digit numbers. And of course that agrees with everyday experience, right? Two-digit numbers, you're talking about 10 through 99. And if you count those up, you'll get 90. So there are 90 two-digit numbers. Okay, let's look at this. Let's say how many are divisible by 5. Okay, so let's think about this, and let's use the counting principles to do this. So I'm going to do this in stages again. I have 2 stages. I want to make a two-digit number. Okay, so I have 9 choices for the first stage. The first stage is just going to be the first digit, and that can be anything. 1, 2, 3, 4, 5, 6, 7, 8, 9. The only thing that was eliminated was 0. Now let's think about the second stage. I want the number to be divisible by 5. And of course there is a very easy way to look at a number and tell whether it is divisible by 5. Does it end in a 0 or a 5? If yes, then your number is divisible by 5. If not, then you aren't divisible by 5. So for the second digit, you only got 2 choices. You can make that second digit a 0, you can make it a 5, and that's it. So that leaves you with 18 two-digit numbers that are divisible by 5. Okay, so a neat little application of the counting principle. If you don't believe me, you can count them up, right? 10, 15, 20, 25, 30, 35, 40, and so on until you get to 95, and you'll come up with 18 possibilities. Okay, let's look at a couple of other examples where we apply the counting principles. So let's imagine a game consists of drawing 4 cards, and we're going to draw 1 from each suit. Okay, so let's imagine the suits are separated into 4 piles. You have a pile of the hearts, a pile for the spades, a pile for the clubs, and a pile for the diamonds. So the question I want to answer here is, how big is the sample space? Okay, well, using our counting principles, we're going to break this task up into 4 stages. You're drawing 4 cards, you got 4 stages. Okay, now each of the suits has 13 cards in it. Okay, you've got the ace through 10, that's 10 right there, and then you've got the jack, queen, and king. So each suit has 13 different cards. I would probably just leave it as 13 to the 4. If you want to, you can use your calculator to compute this. 13, whoops, it's not turned on. 13 power 4, and we get 28,561. Okay, so let's look at an event, right? This is the sample space that would have 28,561 things. And remember, I'm getting that using our counting principle. I'm not listing out 28,000 things. That'd be totally impractical. Okay, I'm using logic to do the counting for me. Okay, so let's look at this here. Count the number of ways an ace, king, and jack can be chosen. Now, I want you to note here in this problem, it didn't say the ace had to be first. It didn't say in that order. Okay, if it was in that order, then there's only one way to do it. Okay, but it just said I'm going to end up with an ace, king, queen, and jack. Okay, so once again I have 4 stages to my problem. I'm going to think of this a little bit differently though. The first task is I'm going to choose where the ace is going to come up. Am I going to put the ace first, second, third, or fourth? Okay, so when I'm choosing where that ace is going to go, I got 4 possibilities. And next thing I'm going to choose is the king. Where's that king going to go? Now, if you decide, okay, we're going to put the ace in the 3rd spot, then you cannot put the king in the 3rd spot. You have to choose from the 3 remaining spots to place the king. So here I'm going to choose the queen. Now once the ace and king are placed, you only have 2 spots to choose from for the queen. And now, when you're deciding on the jack, well, you only got 1 spot left. Okay, so 24. 4 times 3 times 2 times 1 is 24. So this is the event that our 4 cards have an ace, queen, king, and jack in some order. Okay, one more example, and then we'll call it a day. Let's suppose a multiple choice test has 15 questions, and each question has 5 possible answers. So let's imagine you can answer A, B, C, D, or E on each of the questions. How many ways are there to complete the test? Okay, so I claim that there are 15 stages to this. Okay, you're wanting to complete this test? It has 15 questions, so you better give me 15 answers. Okay, so this experiment has 15 stages. Each of the stages can be completed in 5 ways. Okay, you have 5 options for each of the questions. So remember the 15 stages are coming from the 15 questions. And each of the questions can be answered in one of 5 ways. Okay, so imagine that I put down 15 spots, right? In fact, maybe I'll do it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so those are all my spots. Each of the spots can be filled in one of 5 ways, so we have 5 options on each of these. Okay, there's a much shorter way to write that, of course. Okay, it's 5 power 15. Okay, I'm not even going to bother computing that. It's a really big number. I'm just going to leave it like that. 5 to the 15 is the number of ways to complete this multiple choice test with 5 options. Okay, so remember, when you're using the counting principles to answer a question about how big the sample space is, you got to break the experiment up into stages. Think about how many ways there are to complete each individual stage and then multiply.